Okay, my name is Hideo Ohno. I'm from Tohoku University, and today I would like to talk to you about Spintronics, particularly nanoscience and nanoelectronics. What we are doing in these two fields. These are my collaborators. Without them, I could not have done any of the things that I will be talking about today. And the support is given by the Ministry of Education of Japan. Nanoscience and nanoelectronics is a very broad area, but I would like to focus on two things. And I would like to start from nanoelectronics. The first thing is what we can do in terms of Spintronics to overcome the challenges that we are having in integrated circuits, semiconductor integrated circuits. And we are using magnetic tunnel junctions to overcome the challenges. So first I would like to discuss about magnetic tunnel junctions. And then I would like to show how we can use those magnetic tunnel junctions to overcome the challenges that we are facing in terms of integrated circuits. Magnetic tunnel junction is an element that I'm going to discuss or describe to you in the next slide, but it's a non-volatile element. So many people are using this for magnetoresistive random access memory. But what I would like to discuss here is that you can use it as a part of logic, and you can make your integrated logic circuit less power hungry and high performance. And here in the second part I would like to discuss about what comes beyond magnetic tunnel junction. Here we are using current or spin current to switch magnetization. But I would like to discuss in my second part the possibility of reversing magnetization using electric field alone. So what is magnetic tunnel junction? This is our magnetic tunnel junction. It has two ferromagnetic layers separated by a very thin insulator. And this thin insulator is thin enough so that your electrons can tunnel through. And these two magnets are engineered in such a way that one of them is difficult to change its magnetization direction. And the second layer here is a layer we call free layer. Actually, it's not free, but free layer or recording layer, where we encode our information in terms of magnetization direction. So we have two states, these anti-parallel state and parallel state. And these are 1 or 0 or 1 or 0. This is our element. And because it's based on ferromagnets, it's non-volatile. You don't have to supply power to keep the state of ferromagnet. In order to use it in integrated circuits, you have to be able to read the status or configuration of magnetization directions electrically, and you have to be able to write them electrically. And you can do so, for example, the read part can be done by just measuring the resistance of magnetic tunnel junction. These two resistances are different. And here the resistance is low, and here the resistance is high. And you can easily understand it in terms, if you think about a material like half metal. This is half metal, where you only have one spin polarization. Because the tunneling process preserves spin direction, this will allow electrons to tunnel from one electrode to the other. But this configuration doesn't allow electrons to tunnel from this one to the other electrode. So in this case, your resistance is infinite, and in this case, your resistance is finite. But usually what happens is that your material has both spin directions. So the resistance change, although this is low resistance, this is high resistance, there's a certain resistance range that you can switch from antipyro to pyro and pyro to antipyro. And that is defined as here. Antipyro resistance is high, pyro resistance is low, and the resistance difference divided by pyro resistance is called tunnel magnet resistance. So this is something that we would like to make it high. So historically, people have found actually in 2001 there were 2 theory papers showing that even though iron, which is very common ferromagnet, or cobalt, which is another very common ferromagnet, even though they are not half metals like this, you can make it effectively half metal by introducing magnesium oxide, for example. Here, if you have a certain crystal orientation, in this case BCC iron 001 with MgO, this is sodium chloride structure 001. If you can make your electrode or magnetic tunnel junction structure this way, then they have shown that those unwanted states will decay in magnesium oxide faster than those wanted states. What I mean by wanted state is that this state, which is called delta 1 band, is shown here for the iron case. And here, this is our Fermi level. And this delta 1 band has 2 branches, and only one branch crosses Fermi level, which means that if you can forget about other states, iron becomes half metal. And if you look at the structure from this side, these 2 states, which are those black states, are filtered out, and you only see these red and blue states, which means that looking at this side, your iron or cobalt is effectively, you can look at it as a half metal. And in 1995, 2 groups, one group at Tohoku University, another group at MIT, showed that at room temperature you can have a reasonably high tunnel magnet resistance ratio. But what we would like to have for integrated circuit, we would like to have it beyond 100%. Otherwise, the reading circuitry has to be sensitive enough, which means that you have to have more transistors to build your reading circuitry. And that's usually what you don't want to do because it makes your circuit larger and more extensive. But although people worked very hard, we couldn't pass this barrier of 100%. But remember that at 2001, this MgO proposal came out, and people started to work on MgO. And now, 2 groups at AIST and IBM showed that you can have a very, very high tunnel magnet resistance. And we also have shown that even with single barrier MgO tunnel junctions, we can have a rather large TMR ratio. 600% means that your base resistance, if your base resistance is 1 kilo ohm, your resistance change is 6 kilo ohm. So you can change 1 kilo ohm to 7 kilo ohm. So that's what 600% means. So this, the reading part has been overcome. It used to be that TMR is not high enough for integrated circuit applications, but now it has been overcome by introducing magnesium oxide structure. It's nice to point out that you do not have to have a a crystalline structure and epitaxy to achieve this required crystalline structure for this high TMR ratio. This slide shows that this is as deposited state of cobalt iron with boron. Adding boron makes it amorphous. So it's not crystalline. So the bottom part can be anything. You deposit amorphous layer, and on top you deposit MgO by very standard sputtering. But if you deposit unamorphous MgO by sputtering, it has a very highly crystalline structure, which is oriented in the direction exactly what we want them to have. And on top we put cobalt iron boron again, which is amorphous. And if you anneal it, actually this solid state epitaxy takes place, which means that this amorphous cobalt iron boron crystallizes from this boundary, and eventually at high temperature it crystallizes in the structure that you wanted to have. And you can see along with this crystallization, the TMR ratio increases. And this is how we achieved the highest single barrier MTJ value to date. There are many diffusions taking place in this rather complex structure, and we need to avoid those diffusions. For example, in this case, tantalum diffusion was shown to be detrimental in getting high TMR ratio at high temperatures. So in order to show that tantalum is doing something detrimental, we made this thick cobalt iron boron layer thick and reduce the tantalum diffusion, and we have shown that you can even at high annealing temperature, even at a very high annealing temperature, we can get 600%. So although this is not exactly the structure we are going to use for integrated circuit applications, this shows clearly the potential of the structure that we are dealing with. That's the read part. You can read the resistance difference between parallel and anti-parallel state to detect whether you have 1 or 0. You have to also be able to change the magnetization direction. You have to rewrite from 1 to 0 and 0 to 1. And this is done by spin transfer torque switching, which I will not go into details here. But you can, but basically it is due to the conservation of angular momentum. From you input electrons which has the same orientation as this one. This is your insulator, this is your first magnet, and this is your second magnet. And when it passes through the second magnet, it changes its spin orientation according to the magnetization you have here. So it changes magnetization, or it changes angular momentum, and this change in the angular momentum is transferred to this blue arrow. And at beyond threshold current density, you can switch this blue magnetization by this red torque exerted by electrons. So this is how we do switching electrically. So to make a long story short, I have listed magnetic tunnel junction features here. We have high output. As I have shown you, we can easily get over 100% tunnel magnet resistance ratio, which is important for readout of the signal or the resistance. It is non-volatile, depends on the dimension. So, and this is something that people are still working on. But if you assume that we have 100 by 200 nanometer junction, then we can have this energy barrier that separates the two configurations, parallel and anti-parallel, large enough so that we can keep the information there for more than 10 years. And the spin transfer torque switching is being done, and the current density, although we would like it to reduce it further, but the best case we can get 1.5 times 10 to the 6 ampere per square centimeter with this non-volatility. So that's reasonably good. We haven't been able to show the endurance up to 10 to 15, but it appears that we can do the switching close to this number, which means that it is virtually infinite. You can switch it virtually infinite number of times. And this is important too. And I will discuss about back end of the line compatibility later in my slide. And although I haven't shown you this, we can read and write reasonably fast, less than 10 nanoseconds. So this is rather unique set of features that you cannot achieve in other non-volatile memory elements, like flash. Flash endurance is not as good. FERAM, it's rather big, and also it cannot scale down with the dimensions. So this is the only non-volatile memory element that you can use with logic elements that I will discuss, logic integrated circuits that I will discuss in the following. So now we have this magnetic tunnel junction. So let me describe to you what we can do with this. There are two major challenges that integrated circuits are facing. For example, one of the challenges is processor power. This is here. This is taken from Gordon Moore's ISSCC conference, and as you reduce the dimension of your transistor, the circuit gets faster and faster. But along with it, you have to pay more power. But here, the leakage power, or power due to leakage, is also going up. And that's because small transistors cannot turn off as good as large transistors. So they have to, you have very small leakage current, finite leakage current in advanced transistors. But when you have billions of them on a chip, it adds up to a power that is compatible to active. So even your processor is not doing anything, you have to supply a large amount of power. So that's one limit, or one challenge. Another challenge is a delay by interconnection. So this is a processor, rather old Itanium processor from Intel. We have multi-core processors today, but basically the structure is very, very similar. You have processor part here, and actually, although you call it a processor, most of the part is occupied by memory. And you have to load your information from here to there and put it back again. And this is called global. This is done through a global interconnection. This is a slide showing the minimum feature size, basically the transistor size, and the relative delay. As you reduce the transistor, the gate delay goes down because your transistor works faster. And local delay goes down because you have better transistor. But because you put more and more transistors into this processor, the global delay, if you don't do anything, it goes up actually. So even though your transistor is good and fast, your system becomes slower. So that's a delay by interconnection. And also you have to pay power to charge and discharge interconnection, which is also which is another source of power consumption. We can overcome these two major challenges by using magnetic tunnel junctions. first of all, we replace those volatile memories. These are volatile, which means that you have to keep the power in order to keep the information there. But if you make these memories non-volatile, you don't have to supply power unless you want to rewrite or unless you want to read. So this part, if you make it non-volatile, you can save a huge amount of power. So we can make the memory part non-volatile. And actually, we can put memories in the back end. This is a cross-section of an integrated circuit. This is your silicon surface. This is your transistor. And we have to wire transistors to, we have to have interconnect to interconnect transistors to another, to other transistors. But because we are not using semiconductor, we can put magnetic tunnel junction in interconnect. So which means that we can not only make this part non-volatile, we can put this memory on top of the processor. So that means that we can reduce the size of an integrated circuit, and that means that we can reduce the interconnection delay. And in addition, if you can reduce the size of the integrated circuit, that also means that it becomes less expensive. Because after all, you process a wafer, and the cost of processing a wafer is approximately constant. So if you can put more integrated circuits on a wafer, it means that your cost or the price of integrated circuit is reduced. So that's the meaning of memory in the back end. And actually, when you come up with a very good circuit design, you can actually use this magnetic tunnel junction to do the processing. And that means that you can even reduce the number of transistors to do the same function. And that again gives you less, you can do the same thing with less area and less transistors and less power, and it's very cost effective. And this is just a cross-section of our old CMOS transistors with interconnection, and our magnetic tunnel junctions are sitting here. So we have implemented this idea and built a full adder. You add one bit to another with carry. And this is our implementation. The details are not very important, but here we have shown that in this case, we turn off power. And we can immediately resume the operation after turning on the power. You might think this is absolutely obvious because after all, we're using, well actually we're having magnetic tunnel junctions here and there. Well actually we are having non-volatile element. But if you want to do this with other approach, then you have to, when you turn the power off, you have to keep the information somewhere else. So you have to keep the information somewhere else, which takes time and power. And when you start operation, you have to put those information back to the circuit and then start the power, start the operation. So it takes power and time to resume the operation. So, but here, all you have to do is just turn the power off, and we do not need any power here, and we can immediately start the operation. So that's very dramatic. That will have a dramatic effect in power saving. I will not go into the details of this circuitry, but the point here that I would like to make is that your magnetic tunnel junctions are part of a logic circuit. So it means that we can reduce the number of transistors, and actually by this circuit design we can actually also reduce the dynamic power, which is also important. So here we have integrated magnetic tunnel junctions into a logic circuit in a seamless way, and we can reduce the number of transistors as well as we can turn off the power if we do not need to do any addition using this circuit. Okay, so we believe that this approach, although we have just shown a very small element of a full adder, and we have just shown that this is doable, but we would like to extend this approach to show, to go into a more elaborate integrated circuits, and to show that this approach is really power effective in meeting the two challenges that I have just described. Okay, so in the following, let's say, 10-15 minutes, I would like to discuss about electrical manipulation of magnetization. So this is the science part. This is the nanoelectronics part. I would like to discuss what comes after the approach that we're using here. Which means that first of all, we need to change the magnetization direction in many cases. And the first thing we used was a magnetic field. Like in your hard disk drives, we're using magnetic field to change magnetization direction. And if you want to do it electrically and it's less power hungry, you use spin current or spin polarized current that we're using to change the magnetization direction of magnetic tunnel junctions. This is less power hungry than this approach when it becomes a very small magnet. But still, we would like to reduce the power even further. And in order to do so, we would like to look into the possibility of electric field magnetization manipulation. If this can be done in a region, in an accessible, let's say, electric field, in the experimental accessible electric field, we can reduce the switching power quite considerably from this one to here. Now, here I will switch my material to show the principle of the idea. I am going to use gallium arsenide with manganese, which is ferromagnetic at low temperature. So this is our material from now on. The ferromagnetic semiconductor, like gallium arsenide with manganese or indium arsenide with manganese. Here manganese, in those materials, manganese does two things. It gives you localized spins, and it also gives you a hole, because manganese is an acceptor in gallium arsenide or indium arsenide. And interaction between hole and localized spins gives rise to ferromagnetism. And we have shown that we can electrically manipulate transition temperature or coercivity in indium manganese arsenide. But here I would like to point out that this is a valence band of gallium manganese arsenide. And as you can see, it's very anisotropic. We can make it even further more anisotropic by introducing strain. And this means that if you can change the carrier concentration, these spin split bands are there because they couple to orbits differently. So these states are coupled to, have different spin orbit interaction. So if you can change the carrier concentration, we might be able to emphasize this spin orbit interaction over that spin orbit interaction. And spin orbit interaction is the thing that determines magnetic anisotropy, or the direction of magnets. So if you can change the anisotropy, we should be able to see the change in the magnetization direction. So the idea is here, this is our metal insulator semiconductor structure. We apply electric field to change the carrier concentration. And along with this change of carrier concentration, we expect to see some change in magnetization direction. So let's see if we can see it. So this is our sample structure. We have zirconium dioxide, one of those high K materials that people working in silicon have developed. We have 4 nanometer gallium manganese arsenide, rather thin, in order to have a good control over or carrier concentration over the entire gallium manganese arsenide. And we apply electric field or voltage between gallium manganese arsenide and the top electrode. Here, magnetization lies in the plane of our device. So we have to be able to detect the direction of magnetization which lies in the plane. And for this we use planar Hall effect. Planar Hall effect is nothing but anomalous, anisotropic magnetic resistance. So basically we measure the voltage across, and when the magnetization changes its direction in the plane, the voltage changes, and from which we get the direction of magnetization. So here is the result. We first apply magnetic field in plane. So this in-plane magnetic field. We have in-plane magnetic field, and we rotate it about the perpendicular axis, or axis perpendicular to the sample. So we rotate the magnetic field. If you have no magnetic anisotropy, your magnetization closely follows the direction of magnetization. So what you expect is this cosine 2 theta. So this blue dotted line is the line you expect for the materials that you do not have anisotropy. Or if your magnetic field is strong enough, you see that there will be cosine 2 theta. But here you can see that it is not, the black one is experimental data, and when we change the direction of magnetic field, which is 0.15 Tesla, the experiment was done at 2 Kelvin, it's not like cosine 2 theta, but it's, you can see that it is skewed. You can immediately tell that this is easy axis, or that's the axis where the energy, your energy is the lowest. Well, because even though you're changing the magnetic field direction, your magnetization stays there. Even if you change the magnetic field, your magnetization tends to stay there, which means that it's energetically stable. Conversely, this is your hard axis. And if you take a derivative of this resistance here with respect to the angle, you can clearly show that this is your hard axis because it's steeper, and this is your second hardest axis because it's less steep, but it's less than this one, and these are your easy axis because it has the lowest value here. And with changing the carrier concentration or changing the electric field, you can see that this one becomes lower and this becomes higher. So your magnetic anisotropy changes as you change the carrier concentration. So you can quantify this effect of carrier concentration or electric field by assuming that we have this free energy, which is determined by biaxial anisotropy, uniaxial anisotropy, and also this Zeeman term, because we have applied a slight magnetic field of 0.15 Tesla. And using these two parameters as a fitting parameter, we can determine the biaxial field as well as uniaxial field. And as you can see, by changing the carrier concentration, we could not see the change in the biaxial anisotropy, but we can actually see the change in the uniaxial part, and uniaxial part can change its sign. So, knowing these parameters, we can construct, using this free energy form, which direction our magnetization is pointing to in the absence of magnetic field. And this is what we have done. So without magnetic field, our phi, which is the direction of magnetization, is a function of gate electric field, and it changes its direction by, let's say, slightly more than 10 degrees. So this means that we can change the direction of magnetization by just gating our material. So this is the farthest we have gotten so far with our experiment. But this makes us think that what needs to be done in order to do switching. That's something that we want to do. So there are two approaches. One is to control in-plane anisotropies, and the other is to switch in-plane to perpendicular anisotropy and back. This should be able to be done because in many other samples, if you have reduced carrier concentration, we tend to have perpendicular anisotropy. But let me first explain very briefly this one. Here we assume that in our case we have biaxial anisotropy and uniaxial anisotropy, which we do have in our gallium nitride arsenal. Here we also assume that this uniaxial anisotropy, we can change its sign by electric field. We need to assume that we have another uniaxial anisotropy, which can also be, the sign of which can also be switchable by electric field. So this is a big if, but if we can achieve this rather secondary uniaxial, which can be very weak, uniaxial anisotropy, we should be able to do the following thing. So this is our potential landscape, assuming that we have two uniaxial 1, uniaxial 2, and also biaxial anisotropy. And at the minimum here, our magnetization is pointing to this direction. By changing uniaxial anisotropy gradually, which hopefully by electric field, the minimum changes in this way. And when it changes sign, it goes this way. And if you start from here and if you go back, actually it will not go back to its original position, but the trace or the trajectory is different, and you can have a 180-degree switch. So basically what you're doing here is that you're using the anisotropy landscape to form a ratchet motion. So if the product of the two is negative, then it goes the other way around. So if we can achieve this second term, we should be able to do 180-degree switch. Another thing is in-plane to perpendicular and back. So if you can change the in-plane anisotropy, easy axis to perpendicular anisotropy and back, if you make everything, if you make other conditions appropriate, you should also be able to switch the magnetization direction. So what I have shown you here is that other than magnetic field switching, we are using currently spin torque switching. And there are many other proposed ways of doing magnetization switching, like using mechanical stress, light illumination, or using multiferroics. Apart from very fine physics that is being done in multiferroics, one of the goals for multiferroics is to switch magnetization direction by electrical means. But here I have shown you that there is another approach that you can change the carrier concentration, and with this you can change the anisotropy. And if you can control the anisotropy in an electronic way, we might be able to get switching. You might think that this is a low temperature measurement. We are using gallium manganese arsenide. So what about room temperature? What about other, let's say, ordinary materials? It's surprising to see that people are finding out electric field effects in ordinary metals as well. For example, in 2007, group in Grenoble, they have shown that you can change the coercivity of, sorry, it's very small, but iron platinum, for example, by applying electric field. Recently, Osaka University group, led by Professor Suzuki, has shown that you can switch or you can change the magnetic anisotropy by applying electric field. We have also done a similar experiment, which is not published, but we have seen electric field modulation. So, we are hoping that this new approach will give us yet another energy efficient way of doing magnetization switching. So this is the last slide of my presentation. What I have shown to you today is that this spin part, where you can have non-volatile memory function, we are introducing it into semiconductor, let's say, electronics, to make this part more energy efficient and hopefully more with higher performance. The second part, we have shown that by changing carrier concentration by electric field, which is routinely done in semiconductor physics and semiconductor electronics, we might be able to use it in magnetism to change the property of our magnetic materials. Thank you very much for your attention.